But now we are.
Now we are. All right. So, welcome everybody. We're going to start our second lecture for our ECTF team today. So we're going to talk about embedded systems. It's embedded capture the flag. Embedded is the main part of it, or well, something. Anyways, and talk a little bit about embedded security. So, okay, now what is an embedded device? Like, what kind of things will you see embedded in? Hey, Paul. Feel free to take a seat, grab some pizza. Okay, so yeah, you see embedded embedded hardware like everywhere. Your smartwatch, radio, iPod, Apple CarPlay, routers, all the shebang, cool stuff. So what really characterizes an embedded system? So an embedded system is kind of characterized by the fact that it's specialized hardware. It's supposed to do one job, something very specific. It's low power consumption, smaller form factor, real-time operation, which, and then you can customize it, you can reprogram it for the most part. High efficiency, because it's designed for a specific purpose. And yeah, there's like usually I/O, some memory on it, stuff like that. But yeah, kind of the types of embedded systems, microcontrollers. You guys should all be. Most of you guys will be familiar with them, like Arduinos, STM32s, PIC series, that kind of stuff. And then there's SBCs, so kind of on the Raspberry Pi side of things. For some reason, all the SBCs, they love using the word Pi in it. So you have like Raspberry Pi, Orange Pi, Banana Pi. But I don't know what that's about. But yeah, you have these things called FPGAs. So at IEEE we have a project called DAV, which talks more in detail, or you'll cover these things. But these are like reprogrammable kind of logic gates. So it's pretty cool stuff. ASICs, application-specific integrated circuits. So for the most part, your microcontrollers, SPCs, they have some. They'll come in some different form factors, and they'll be reprogrammable. But your ASICs, those are chips, and those are pre-programmed. For the most part, their application is set. System on chip, it's just like a bunch of different systems. So your memory, your processing, all that stuff. So you have stuff like Qualcomm, Exynos, all that good stuff. But yeah, I guess. Yeah, those are mainly the kinds of embedded systems. We're mostly going to be dealing with microcontrollers. We'll talk about the one in specific. There's one over here. This is TI Launchpad. This is what we're going to be dealing with. But yeah, what defines a microcontroller is usually it has like the processing unit, it has some memory, it has some input-output. You can program these things, so pretty cool stuff. The processing unit, it's again programmable. So you're characterizing microcontrollers. If you have ever heard of my STM32 is a 32-bit microcontroller, or Arduinos, those are like 8-bit microcontrollers. It's kind of like what the size of the chunks are. There's also the clock speed. There's architecture sets. There's wired communication. So all of this stuff is happening on a processor level. So clock speed is kind of, so if you guys have heard of complexity, algorithm complexity, that depends on things like clock speed. So it's kind of like how many operations you can handle per second. It's a little bit more complicated than that, depending on parallelization and stuff like that. And some operations, they'll have different times to them. So there's simple operations like add. Like addition, that's like a single, cycle, but other applications might take some more time. So the architecture, there are different types of architectures. Mainly, again, some of this is a little extra information, but to some extent, like the architecture is like, okay, what kind of instructions do you have? So you have things like addition, multiplication, carry. We're gonna kind of see what that kind of looks like. I'm not gonna go too in depth on it. But it's important if you're going to be doing things like binary exploitation, if you guys came to the other workshop. And then there's some wired communication stuff. So, serial communication, so SPI, UART, I2C, if you guys know what all that's about. That's basically how do you have two different devices communicate with each other. So let's just say I have my Launchpad and I have like an Arduino Nano. You kind of want to communicate between each other. You'll usually be dealing with one of these communication protocols. If you guys know what an HC05 is, that's a Bluetooth module. It's usually you pair those with an Arduino that deals in UART. We're going to talk a little more about that in a second. For some reason, I don't know why this came here. I should probably have gone into this slide before talking about all of that. I guess let's just skip ahead really quickly here. So again, what characterizes all your different serial communications is kind of usually UART. Again, this is a little bit more information. Some of this might not make sense until you start actually playing around with these things. But UART is just point-to-point communication. It's kind of asynchronous, so there's no clock signal being sent. SPI, this is communication usually between like a primary device and a secondary device. Sometimes people call it master and slave. And I2C is communication between multiple primaries and secondaries. So stuff like that. So then again, you have after that, in your peripherals and your input-output, you have things like analog and digital converters. So you have analog to digital converters. So that's going to take your analog signal, convert it to a digital signal. Okay, so before talking about that, let's talk what is an analog signal. Does anybody want to take a stab at like what an analog signal is? Anyone? Yes.
Is a signal with continuous values rather than discrete?
Yes, it's a signal with continuous values. That means that it can take on a finite number of values. It's like, okay, you can have 3.235 volts, at time t is equal to 0, and then 4.145 volts at time t is equal to 1, right? That's a signal that's changing, but it's just like, it can take on any value. Let's just say it's capped between 0 and 5, that's still not a discrete number. It's like, it's an infinite number of values it can take. So it can kind of be like a varying, voltage level, something like that. That's an analog signal. Your digital signals, it's gonna kind of how you encode that analog signal into a digital signal. So if you have, let's say you have your analog signal, let's say you want to digitize it and you want to have 8 bits of that signal. So what 8 bits, that's 256 levels. That's like 0 to 255. So if you guys know how like RGB colors work, RGB colors are kind of like your digitized signals. So you have 255, 255, 255. So that's 8-bit on each of the channels. 255 being full or max on that color, and then 0 being darkness on that color. But yeah. So if you guys want to know more about how like the analog to digital conversion actually works, it's kind of interesting. It's these things called resistor ladders. Pretty cool stuff. But yeah, so you have analog to digital converters. You have DACs. You have digital to analog converters. So you know how we construct our analog or digital signal from our analog signal. Now we're going the other way around. So we have our digital signals. We have our ones and zeros that represent different levels of some signal, and we're just going to convert that usually into like some form of voltage signal. So that's a DAC. The thing with analog to digital converters is you'll often see those on microcontrollers. You will often not see a DAC on a microcontroller, and that's like, you might be wondering, okay, like I know I can take analog input on an Arduino, but I also know sometimes if you guys have played around with Arduinos enough, you might know that you can actually change, like if you're driving an LED, you can make it full brightness, half brightness, stuff like that. And that's actually not done with the DAC. That's done with this thing called pulse width modulation, PWM. So again, I probably should have put this on a slide there somewhere. So let me bring it up really quick. But kind of what a PWM signal is let's bring this up here. Okay, so you kind of have your digital, so you kind of have your varying voltage signal, so some analog-esque signal, and you kind of want to represent it with a digital signal, because that's a little bit easier than doing a full DAC conversion. So what you do is you have different pulses. So this is like one pulse, this is another pulse, this is another pulse, another pulse. So you have multiple pulses, but the duty cycle, if you guys know what that is, duty cycle is kind of a pulse is it's an on signal and then it's an off signal. So if the duty cycle is 100%, that means it's going to be on for around 100% of the time and off for 0% of the time. So in this case, this is kind of like a duty cycle of 50%, so kind of half the power. So this goes on, it stays at here for 50%, goes off, something like that. And that kind of represents this part of the signal, you know how it's like half, so half of the like total power. So yeah, that's usually what's done when you want to kind of emulate an analog signal. And then yeah, so those are most of your interfaces. You also have general purpose input output. So those are like just your general pins. So if you are familiar with an Arduino, your digital pins, those are general purpose. They can just be configured as a digital pin. You can make it do kind of whatever. You can drive it to 1 or 0, or you can read input from it. So stuff like that. And then yeah, I'll go back to memory because I didn't talk about memory. But on your microcontrollers, you have a couple of different kinds of memory. So you have your read-only memory. Read-only memory is kind of, well, it's what it stands for. It's read-only memory, right? Your ROM, it's not memory that you can manipulate while you're running your microcontroller. Usually you store things like firmware on it. So again, it makes sense because you want, it's also non-volatile. Volatile versus non-volatile. Volatile kind of means that, if you turn off your microcontroller, if you unplug it, the memory's gonna go away. And if you keep it plugged in, then non-volatile memory is gonna stay there. Volatile memory will stay there, otherwise it's gonna be gone. And kind of the difference is, it's kind of a trade-off. Your volatile memory, okay, it will go away when you turn it off, but it's also faster to access. So if you have some memory where it's like, okay, you're doing some computations and you want to quickly store some piece of information to access it within that, within a short period of time, then you're going to be using your volatile memory because you don't really need it after the program's ended. But yeah, your non-volatile memory is stuff like firmware or some storage. So you want it to stay there even when the program's off. But the trade-off you're making is it takes a long time to read from it. So yeah, and then yeah, there's two different kinds of non-volatile. You have your read-only memory. That's your firmware. So you don't really want to be writing onto your firmware while you're running your microcontroller. So that's why that's read-only. Your flash memory is non-volatile, but you can write onto it. So it would be things like if you're storing, for some reason, if you're storing pictures on your microcontroller, that's going to be on flash memory. So it's going to go away. It's not going to go away after you turn off your microcontroller, so you can access it whenever. But yeah, so again, analogous for those of you who have used Arduino Unos before, just because it's like an easy example to pick from. You can kind of see the properties of, well, your microcontrollers on an Arduino. The architecture, it's kind of an 8-bit RISC architecture. Talking more about, if you guys remember, I was talking about like your instruction set. This is an instruction set over here. Again, you don't need to worry about all of this unless you're trying to do some form of binary exploitation. But you have like arithmetic, you have bit manipulation, all that kind of stuff. Yeah, and then memory, there's some flash memory, there's EEPROM, which is your storage, and then you have your SRAM. And then yeah, I guess, yeah, that's mostly it. That's kind of how the chip is designed. Again, you don't really need to know this for now, unless you're actually working on some sort of side channel. But just kind of as an overview, that's for the most part all you need to know. Kind of on the peripheral side of things, you can kind of see your GPIO pins. So all your digital pins, those are general purpose. You can use them for whatever. PWM pins, so if you have tried running LEDs on Arduinos and tried making them variable brightness, you kind of know that that some of them don't necessarily work. So your PWM pins on the Arduino are marked with the tilde. I2C. So there are some dedicated I2C pins on the Arduino. There's the SCA and SCL pin kind of on the top. And then there's, for SPI, there is this dedicated header over here. And then UART is your pin D0, D1, TX-RX. Analog to digital converters, these are all ADCs. Again, nothing you guys really need to remember, it's just like this is the general kind of how an Arduino works. We're going to be working with these guys, so again, don't worry about this. But yeah, now if you want to talk about this board, so this is the stuff we actually care about.
Hey, yeah, so I'm going to talk a little bit about the board that we're probably going to be using for ECTF, or at least the past few years in ECTF have used this board. So yeah, it's an ARM microcontroller. It's from Texas Instruments. The part number is right there. It's got like cute nickname Tiva. The launch pad is the dev board itself. So we're gonna dive into the data sheet for both the chip as well as for the dev board and take a look and see what kind of information we can find there. So yeah, we have the eval board is nice because it allows us easy access to the I/O, so you can do embedded systems development just like will be done in ECTF. So yeah, there is the data sheet. I have it linked here. I'm going to pull it up in a bit, but we're also going to go through it a little bit. It's very long, over 1,000 pages. You don't need to read the entire thing because a lot of it just has way more information than you do need to know. But it's very important to know that all the information is there. And it's actually better when it's longer because it means that it's well documented instead of it being short and being unable to find anything. But anyway, as you might imagine, it's very long, might be a little bit difficult to navigate at first, but there is a lot of great information there. Really kind of the most important part, and that's what we're going to be looking at today, is kind of the one of the very first sections of the data sheet. It's like the overview, and it kind of talks about what different features that the microcontroller has and what it supports, and so that's really what you want to look at when you're, well, for one, choosing a microcontroller. If you're evaluating different options, say there's this TI board and you're looking at something else from ST, or who knows, something else, or you're looking at multiple different TI boards, you want to choose something that is appropriate for your purpose, which could mean clock speed, could mean something about certain peripherals. There's a lot of different factors there. So all that information really is all summed up in the data sheet in full technical detail. That's where you want to look. And that is the same thing. Okay. Yeah, so here's one of the pages of the data sheet. I lied about it being the first page, of course, because it's actually the 46th page. But it is one of the first useful pages that you will encounter when you open up this data sheet, or at least immediately useful, I should say. Let's take a look at just this top part. This is like information about the performance, as well as information about the storage. As you can see, we have RAM, as well as EEPROM and Flash. And so we actually use Flash to store the program. And so that's both Flash and EEPROM are going to be like sort of maintained after you reset or power cycle the chip, whereas anything in RAM will be cleared. And RAM is where you'll do most things when you're actually writing programs. And so yeah, as you can see, it is an ARM board, so it'll use the ARM ISA, and it has a 80 megahertz clock speed, which is quite a bit more than Arduino, if you remember what Sanjay was talking about earlier. So this talks a little bit about communications protocols. Sanjay kind of already gave a rundown, but as we can see, there is support for most of them. We also have CAN, which is an automotive standard, which is kind of interesting, not necessarily super relevant for ECTF. Although last year it was car related. It was unlocking a car, so I don't. But still. We have some other kind of features within the microcontroller itself. DMA is direct memory access, and so that's super useful for when you're doing some things on embedded systems, because you're able to transfer memory without using the main, without making the main processor busy. So you can kind of asynchronously transfer things either within the chip or from, say, some peripheral. So that's very useful. There's also lots of GPIO and output. There's also timers. Timers are good for timing things, but also for counting things. You can increment a timer, and so that's a useful feature. And there's also watchdogs are important if there's going to be any timers things that should happen that don't happen, and it's a good way to recognize that you're in a failure state and decide what to do using an interrupt. So yeah, more on the iOS side, but for analog, ADC, many other things. This is the package, 64 pin, not too bad to solder, but thankfully we have dev board, so we don't have to solder. This is another page from the datasheet. This kind of has a lot of the same information that we already looked at, but it's nice to see it kind of in a, I guess, graphical format. So if we kind of take a look at that, we kind of see some other things. We do have a floating point unit, which is nice. Don't have to be stuck with those ugly integers when doing computations. So yeah, here's some interest. I wrote the acronyms for some things that we have here. We can do, it has good support for debugging, so you can set breakpoints and do lots of helpful things when you're figuring out why your code isn't working. That you can use interrupts, which are super useful when you're dealing something with sensors and you have some input that's going to come at some time, just to name an example. And then yeah, plenty of GPIO. Scrolling down a little bit more, we have good support for motor control, both PWM generations to control motors at different speeds, and encoders to see how fast those motors are spinning. Yeah, so I guess that is what I've kind of the content I prepared for the datasheet, but I do want to just open it up for a second, just so that you guys can look at it and get vaguely familiar, because it may be a very useful resource when trying to understand what this chip looks like and how we might design a secure system. There we go. Yep, so as we can see, a whole lot of pages. There's a nice table of contents where we can click links and it'll bring us to useful places. But we're just going to keep scrolling just for fun. Look, there's a lot of descriptions of all these registers that are on the board. So if you ever want to know anything, it's in the datasheet.
Yeah, I'm going to send the datasheet to general in case people want to scroll through it.
Revision history,
On their own.
kind of interesting.
Yeah.
So we got to keep scrolling, and then eventually, oh, this document conventions. Okay, sure. We finally get to part one. So this is what we were looking at here, which here's the capabilities are listed here, and here's that chart that we're looking at. But yeah, if you want to go in more detail, because all that's pretty system level, pretty high level. You can dive into, there's separate sections for basically every single one of those things that we talked about, and the ones we didn't. So you can look here, learn more about the processor core, learn more about the timers, learn more about the memory protection, lots of interesting stuff. And that's all, if you go to the table of contents, what they've done is really nice, is that you can actually, once you get there, click anything. So say we wanted to get more information about the JTAG interface, which is used for programming, we can click here, and we can learn more about it. Lots of interesting stuff. Anyway, I'm not going to go through the entire data sheet because we will be here for several weeks probably. But that's, again, really important to know it's here and to know how to refer to it, because if you need information, that's the first place you should look. We were here. So yeah, that's all just for specifically the chip on the microcontroller. It's right here in the middle. But we also have these dev boards, which are very useful, and they provide a little bit more interesting features, or at least ways to interface with the chip. So there's also another eval board user guide that is thankfully less lengthy, but is also worth checking out. And so here we have, like, you can look at the board, and we have like lists of like where all the pin headers and what they do. Very, very useful stuff to know. If you want to actually use this board specifically, you need to use this data sheet. And then, yeah, just kind of talking about some of that content, but not going into too much detail. Here's some of like the advantages of the board, or some of the features at least. We have some built-in user buttons, which are really nice to be able to do some input to the board for debugging. We also have a user LED, I believe it's here. You can program that without having to connect anything to the board. Here's the chip itself. We also have another chip. This whole side is actually the programmer. So you can connect with that over USB and use that for debugging and for flashing new code. And we also have a bunch of pins here. And so that's where you would connect all your I/O.
Wait, they have two of the same microcontroller on this?
Yes, but one is for the debugger, and one is actually the one that you are programming. But it is very interestingly the same chip. Kind of cute. Yeah, and so this is just another. This is a view of like what each pin does and kind of some of the features of each pin. This actually isn't from the data sheet. This is kind of somebody's. Somebody made this as a way to kind of present the information in maybe a slightly more friendly way. So it's nice to look at it. We can see which pins have like I2C, which pins have UART, and just like which pins are general use and all their different names. Yeah, it's kind of a useful diagram to have when getting a sense of which pins should be used for what. Yeah, so that's it for the TI board. Now we're going to hear a little bit about some embedded system attacks.
Yeah, so the goal of ECTF, we gotta capture other people's flags. So the only way we can really do that is by, attacking their embedded system. So one main part is side channels. Side channels are an unwanted artifact of computation. This can be timing information, power consumption, EM leaks, and acoustics. So a side channel attack is based on that extra information that's gathered because of just the fundamental way a computer protocol or algorithm is implemented. So a good way to think about this is just like I had a piece of paper in my hand. You want to understand the contents of it, like you're understanding it by the way I'm flipping the pages, the vibrations or the sounds, or my reactions to this paper. You can't really see the contents, but you want to find out what it is. And that's a good way to think about side channel attacks and side channels in general. So first, one of the earliest side channel attacks was through EM, electromagnetics, leaks and waves. Proof of concept attacks have been performed to reconstruct user keystrokes from an audio recording of user typing. Some ways to prevent side channel attacks. There's some really intense ways, but as intense as you go, you have a lot of extra things that come with it. So it's a really hard gray area that comes in. It's like, do I want to defend it, or am I wasting too much resources on defending it? So yeah. So just to get more into details, Scott's going to talk more about very specific side channel attacks.
Yes, so as Benji mentioned, so side channels are basically information that you can extract from a processor, a controller, some sort of device that isn't supposed to be a vector for getting out information. And one of those things is power usage. So for example, if you have a processor running two different loads, maybe one's pretty light, you're just doing some additions, and the other you're trying to like mine crypto or something. If you're looking at the battery usage, you'll notice that both of those are very different, right? One's going to be drawing a lot more power than the other. So that's kind of a macro level. But there's also research papers out in the field that are like pretty small granularity. If you're measuring power usage in the time domain, like in the order of clock cycles, you can see that when you have a cache miss, and you have to go into memory, you can see that there's more power used there than when you have a hit and you just pull from a register. So by looking at just power usage over time, you're able to make determinations of like, for example, what branch control flow took when you're running instructions. And you can kind of infer what kind of data was in registers based on that. This was another fun thing. There's a research paper that if you had your phones connected to different wireless chargers and you were browsing one of 10 websites, the data set, the scientists were able to measure the power usage from the wireless charger. So not looking at your phone at all, just the wireless charger and how much it's drawing, and basically determine exactly which of the 10 options you were browsing. Because the power signatures from those 10 websites are different. So that's another example of like how much unintentional data your device could be outputting by power or electromagnetic side channels. So Benji also mentioned EM side channels. If you're curious how this sort of works, you have like a data path in your processor. You might be familiar with this if you've taken like 151B or 116C. So you have a bunch of logic gates, you have an ALU, and your data is stored digitally, typically, when we do math on it. So you have high and low voltage, and then when you want to do math, you pull some data and you put it through your ALU. On the way, it's going to go through a bunch of different gates, and those gates are going to flip the intermediate values. So you're going to have lots of voltage fluctuations all over the place. This causes like little electromagnetic side channels, so blips that are different based on what kind of data is moving through, how much of it, what part of the processor or SoC it's going through. And even though these seem like kind of chaotic and hard to predict, they're actually very deterministic. So that means that, and we'll have a demo for this in a bit, but you can actually use these side channels intentionally. A couple applications. Professor Sahatbakhsh's lab has one application where they're able to take a microcontroller and write code that has a very specific EM side channel, and they can basically use chirps in the EM spectrum and basically communicate as if you have like a low power radio, and you can pick it up with like an antenna. So that's something that you could have a microcontroller running code that maybe you're not exactly sure what it does. You're sure that it's doing the task you asked it to, but maybe it's doing some sort of weird memory access on the side that you have no idea as a user what's happening. But the side effect is that someone else can be reading those side channels, and maybe it's actually transmitting some of your data by that method. So those are a couple applications. This is not a side channel, but this is another sort of attack that we're opened up to, and it's hardware Trojans. So this is probably not a big deal for this particular competition, but just for breadth of knowledge. Oftentimes you buy a board or a chip, but sometimes you ask someone to make it for you. So you have some design in mind, you want like a very specific digital circuit that does some application, or you pay a company to design a board for you. And again, it could do exactly what you want it to, but you don't know that it's not doing more than that. So for example, you could have a module in your chip. So let's say you have a design, it does everything you want, maybe there's a function or some other part of the chip that's doing something secret, like leaking your encryption key using side channels. So that's a possibility. Another more trivial to implement one is like if you have something on your board or on your chip that's just doing a bunch of garbage, it's going to be draining power. Oftentimes for embedded applications, this is like health tech, right? You have like something that you're wearing or something that's somewhere that you don't want to like consistently charge or plug in. So like that type of attack can be pretty devastating. So that's chip level, board level. As Dominic mentioned, the chip is a little thing on there, but there's all sorts of other stuff on the actual PCB. And if you're not aware of what's supposed to be on there, just ask for a board and someone puts another module on there that does something. You could have hardware Trojan on your board. So there's also board level hardware Trojans. So this slide's sort of like an intersection. So this is something else that Nodder also works on. Because side channels are deterministic, and because we can have hardware Trojans that do things we don't want it to, we can actually model what the side channels should look like, and then when we get our chip or board, we can look at what the side channels actually look like and see if there's a discrepancy. And if there's a lot more activity, then you know that it's doing something that it's not supposed to. So there's a couple different research papers on this as well. One's pretty interesting. It's like, I think it's for like power networks or something. It's like a microcontroller that's supposed to be regulating some sort of stuff. And it's not something that you can like easily go over and like probe to make sure that it's doing what you want it to, like with a debugger or something like that. But what they can do is they can measure the EM side channels and they know what it should look like in normal control flow. And so if something bad happened or it's like being hacked or something like that, those side channels will look different. So there's a research paper on using that as like an error detection mechanism, basically looking for faults and stuff like that. You can also use it to identify hardware Trojans. So for example, something that Nodder's lab does is you have like a processor or something, you run code, and based on like what kind of instructions are running and what kind of design you have, the side channels are going to look a certain way. There's all sorts of math behind it. And if you add something that maybe leaks bits or leaks power, or you do some other sort of attack, you're going to see a very different signature. So that's another like active research field in this field. So the benefits of using side channels to sort of debug or look for Trojans, it's really like expensive time-wise to dig into hardware, right? If you're given a microcontroller and there might be a hardware Trojan, maybe not. In order to like find it yourself, you basically have to destroy the microcontroller and like try to go into it and see exactly what's there. But by using a model and looking at side channels, either power or EM, we're able to do that without destroying the microcontroller. Lower cost, and it's a lot easier to test at volume. It's a faster process. Like I mentioned, you can do wireless monitoring of runtime. In fact, one of the things Nodder's trying to do now, or he was last year, is doing some sort of like debugging over not really Wi-Fi or anything, just using side channels to debug. So for example, if you write this like hook into your embedded code, and whenever you have a fault or something, it goes into this hook and you have a function that maybe does like a really quirky loop and generates a specific side channel. And if you're looking at those side channels, you know you have a fault when you see that little squiggle. So that's another way that these can be used. Again, plenty of research happening, especially at UCLA. So last thing I want to talk about, this isn't directly related to side channels either, but it ties a little bit into the importance of data sheets and knowing what's in your embedded platform and what that system architecture is. So you guys are probably familiar with the Rowhammer attack. This is like one of the most well-known ones. This one is basically based on the way DRAM works. Every time you read or write DRAM, you basically have to delete the whole row and you rewrite it in. So DRAM is like a volatile storage. There's voltages in there, and they like slowly leak over time, and they're eventually refreshed. But if you read a row, it's going to cause slight variations in the row above and below it. And until those rows are refreshed, the voltage levels are just going to get more and more off from what they should be. So that's basically how a DRAM attack works. Rowhammer attack works. The reason that data sheets are helpful is you might have seen a glimpse of when Dominic was scrolling. You know that the TI board uses the Harvard architecture. All that means is the instruction memory and the data memory are separate. So you know that you can't do a Rowhammer attack on the data using using an instruction address repeatedly. That's kind of out of the question because they're in separate locations entirely. So going through the data sheet and knowing things about like your memory architecture and stuff like that is really good for both for being able to do defense, but also in the later phase when we get someone else's design, knowing where to look and probe. Last thing, this one's just like interesting to me, probably not applicable, but a lot of modern processors, this is an Intel platform attack, have something called like an enclave, memory enclave. It's like a secure part of the thing that like normal applications can't use. So in this case, it's like a memory enclave. Any data in there is like highly protected. No application can use it. It's like very specific system tasks. But in this platform, you can also adjust the voltage level and clock speed, like through the BIOS or the operating system. And there's a way to pick a kind of unstable pair, and basically cause timing violations in your chip and metastability, and then you can like corrupt the data in the memory enclave. So that's something just interesting. But even if something is technically secure, know that the underlying technology, DRAM, voltage, clock speed, can pretty much always be used to mess with things. And this slide is back to Benji, I think.
Oh, great. Yeah. So basically, timing attacks. So we have side channel attacks. We have some timing attacks. Timing attacks are basically like you have your operations. You're running some program on your microcontroller. Their set of operations, and basically based off of the time it takes for set operations to happen, you can kind of understand some things about your system. We'll kind of talk a little, kind of have a better example in a second, but it's kind of like you're trying to figure. Some of the attacks are okay. Let's say we have some input-output pair, or some. Let's say we're trying to break into some kind of safe, or not safe. Let's just say some password key thing, and we try to measure how long the program faults. So let's say we're trying to break in. So we have a couple of wrong guesses, but we based off of the measurement of what our time or how long it takes for the guess to be returned as wrong, we can kind of figure out a little more about what the password actually might be. But there are a couple of operations in specific that can kind of leak this kind of information. So it's like memory access, conditional jumps, and math. So kind of looking at some pseudocode per se, there are a couple of different ways you can kind of induce or cause a timing vulnerability. So if you're trying to compare strings, if you look at this function, what we're doing is, let's say we have some let's say string 1 is some kind of password, and string 2, again plain text, but string 2 is, say you input a password to some kind of lock, right? And you're trying to be like, okay, if string 1 and string 2 are equal, so the password is equal to what you actually entered, then that means there's authentication, so you allow access. So kind of in this function, what you're doing to compare your strings is you're going through each and every character in the string. So let's say the string, let's say the actual password is password, great password, and we're trying something like A, B, C, D, E, F. So what's gonna happen is we're gonna be like, okay, for each index in string length, right, A, B, C, D, E, F, first index, we're gonna try to compare string 1 of that index, string 2 of that index, so A, B, C, D, E, F, and password A and P. So we're gonna compare those two. Those don't really match, so that returns false, and it breaks out of this function. And we can kind of time that and be like, okay, since that happens instantly, we know that our first character is wrong. So then you modify your first character until, let's say, you get to PBCDED, okay? And now when you go to PBCDED, you do the same comparison. P passes, but B doesn't, so it returns false. But the time it takes to return false, it's a couple of operations later. So you can kind of tell that, okay, my P was correct, but B was wrong. And then you kind of permute that, and you can kind of figure out, what the actual password is. Similar thing with this thing. Instead of that, based off of the fact that we're changing this validity over here, that's going to be an operation. And if this operation, when you hit this operation, you know that you kind of know that. So even though this is a little more secure because it loops through the entire thing, so it is going to take some amount of time. So it's going to take the time that the loop will take. But then if you're doing the string comparison, or if you're doing the character comparison, based off of whether the character is different or not, it's gonna enter this operation, and that's also gonna change the time. But for something like this string comparison, you're kind of permuting validity, so it's always running the same number of operations regardless of whether the strings are the same or not at a certain index. So yeah, that's kind of one way to think about timing attacks. And I guess on the replay side, if you want to talk about that.
Yeah.
Yeah.
Can you go back to the previous?
Uh-huh.
Why is the second column and third column both not O of n?
Both not O of n. Okay, you know what? That's a good point. Again, I'm not a CS major here, so probably should not have tried writing stuff like this.
Or
It-
sorry,
it's-
I guess my question is more so, if they both go through the entire length of the
Yes.
string, why is column 2 vulnerable?
Yes. So O of n, both of them are gonna take like n number of or they're gonna be of complexity order O of n. Or I guess all of them are gonna be O of n because it's a loop. So it's always gonna be O of n. But the thing is over here, basically let's let me think of a test case really quick. So we kind of based off of the fact that, let's say we go back to our ABCD and password. If we compare ABCD with password, the first index is not gonna work. Okay, actually let's go to PBCD and then password. So the first index it's not gonna check through, and you're gonna assign false to validity. So you're modifying this. This is gonna take some time, on the CPU. Versus if in the first, since P and P are equal in the first character of the string, these two are equal, so it doesn't really go in here, and that's one less operation.
Oh, I see. Is it because we always estimate like the branch not taken rather than a branch taken?
Yeah.
Okay.
Yeah, and then after that, basically you can kind of, based off of that, you can kind of figure out how many characters you have right versus wrong, because the expected time, if you had all of the characters being right, it's gonna take probably n less operations per se, n less times whatever the number of operations for that, and then yeah, cool. And then we talk about replay.
So last attack that we'll discuss is replay attacks. So replay attacks are a form of network attacks that will maliciously either intercept or delay or send back the data. So one example here is, let's just say we have Alice, Bob, and Eve. So let's say Alice wants to get access to something through Bob. Bob asks for a password, right? She's like, okay, here's a password, but you have Eve who's sniffing through. It's very passive in nature, so it's not, you're never gonna really notice it until something happens. So Eve's gonna hear the password, nothing's gonna happen. Alice and Bob's exchange goes very similarly. What happens after is that Eve can now interact with Bob. Now that Eve has Alice's password, it's just a normal interaction, pretending as if she's Alice. So it's very passive, but it can be very malicious in nature. One example is keyless fobs for cars. So one thing that was ECTF last year was all about cars and keyless entry. So let's just say I put a jammer that blocks in RF signals near a car I want to get into. If I'm able to block those RF signals from a receiver that's legitimate, if I'm able to block the signals and receive the signal, the unlocked signal, I can then block it and then recreate it to get entry to a car. So very important, very very passive too, very very nice. So yeah, and then with that, I think we have our. Thank you all for attending, and then we have our demos.
Yeah. So for demos, I guess should we have it facing?
Yeah, but I want to show the video first.
Okay.
Yeah, so I guess before we dive into demos, does anyone have any questions? I know we kind of just info dumped for an hour, and some of the info was really just an info dump, especially in my section. But does anyone have any questions?
It's hard to believe.
Don't be shy. Okay. Yeah, so here I have a comment on the slide. Where's my mouse? Okay, so I guess some context before we watch this video. This is from Professor Sahatbach's research, and specifically the project was one of the people that worked on the project was Tim Jacques, who many of you in IEEE are very familiar with. He's our project manager. But what the project is you can actually, so we talked about side channels and how you can observe side channels, specifically electromagnetic side channels, and they'll look different based on what a processor is doing. So this research topic, what the idea was to write programs that deliberately kind of create different side channels and using that to communicate information. And that's, Sadat mentioned this briefly, but this is kind of that research work. So we have a video of it here where we can see it super well. And we also have over here a spectrum analyzer, a near field probe, and an Arduino running some code. And so we can actually show a demo of it looking different for two different Arduino programs. But let's watch this video real quick. There's actually, the code has been written such that there are actually chirps, meaning increases or decreases in frequency that you can actually observe in the frequency output. So here it's running, we're gonna zoom in right there. And so we can actually see that the frequency is increasing and decreasing. And so right now it's just kind of increasing and decreasing, but they've actually written the code such that you can use that to basically transmit information. Like you can have the different waveforms represent like different characters or different types of information. So yeah, that's like the video demo, and if you actually want to see something working on the spectrum analyzer, we have that too. Yes, Andre?
Wait, what are the chirps being generated, or like, what's the chirp signal on?
What do you mean?
Like what data line is it going through?
Like what are we actually plotting?
What are we like measuring on the EM?
Yeah, so this is using a near field probe.
Mm-hmm.
Really, it's kind of just works like it's a really small loop antenna, and you can put it near. Instead of like normal antennas measure the far field, this measures the near field of electromagnetic radiation, and so you can look at an Arduino or some other microcontroller. This was done with Arduino, and near either the clock speed or a multiple of the clock speed, if there's harmonics, you should be able to see. You should be able to see the clock frequency, and then you should also be able to see like some variations around that clock frequency that are generated based on what the microcontroller is doing.
And the chirps, is that like something? Like how did the chirps occur? I guess.
Yeah. So Tim's code actually does something very interesting, or Tim and Justin, I should say, where it basically has for loops, and the amount of time that it takes for the for loop to execute is varied, and depending on how long it takes, that will result in a different frequency. And that's kind of how they're able to generate specific side channels.
Cool.
Yes?
From what kind of distance can this like electrical noise be measured?
So using the near field probe specifically, very near, yeah, if you were to do your Maxwell's equations, it actually like decays at a power of 6, which is quite rough. But yeah, so you have to be quite near. But of course, there is other electromagnetic transmission. So you have to be very near to get it very clear. But if you're a little further away, you may be able to still observe some things. I don't know the specifics. This is. Maybe Sadat would know more, but
I'm looking at the paper right now, but they were able to basically do like a LoRa thing, and even get decent signal at 15 meters.
15 meters. Okay,
15,
wow. So
that's
that's quite
That's
impressive.
pretty good.
Oh well. Okay.
Yeah, I guess the paper, or at least one of the papers that they worked on was specifically for LoRa, which is like a long range. Basically, you can do like relatively long range, low power, and really slow communication. It's like a standard for that sort of thing, and so they were actually able to achieve that type of communication with using side channels. Anyway, that's it for this video. we have the demo set up here, and we can show kind of, depending on what this microcontroller is doing, the frequency spectrum looks different. So I guess that's like the end of our presentation, but if you guys want to come check it out, that would be cool.
I don't know if we should bring the cam for this or.
Yeah.
Okay.
Oh, so I should
Yeah.
Earlier right now.
I just joined it.
Oh yeah.
If anybody has to leave,
Can somebody
please,
put
I've
this
got a
cam
form
on?
that you need to fill out for like doing stuff. Regardless of whether you have to or not, it has to get turned into the department. So that you
So
work
this
so
Yeah, there.
please fill
Yeah,
that
sure,
out when you
check.
guys pass on lunch.
Wait, you need help? Great, is it good?
There you go. Should be good.
Okay.
Oh wait, why is it facing? There you go.
Okay, so
Do you want me to put this up? Can you send it to me? I'll put it up.
Oh, nobody has edit access except for
Yeah. Okay. So is it like QR code or?
Yeah,
It's
it's like
like
a
this-
internal document.
yeah, it's just like this
Oh,
document that
okay.
we have to fill out every time we get food.
Fine.
Great.
Pain.
Yeah.
trying to use
Anyone
the
wants to
spectrum
fill it
analyzer
out?
upside down. So anyway, this is a spectrum analyzer. We are plotting what a signal looks like in the frequency domain, so at different frequencies. Again, we have our near field probe here. Right now it is not near anything, so we see in our spectrum analyzer it's pretty flat at the bottom, as well as right here this is a spectrogram, so that we're plotting the different frequencies over time. It's all blue, meaning that we aren't seeing anything, so as you might expect. Anyway, if we actually go ahead and hold it near the microcontroller, which is right here on this Arduino board, we can actually start seeing a peak right here. And so right now we are at 16 megahertz, which is the clock speed of the Arduino. So what we're really seeing here is the clock frequency. And right now the Arduino is doing nothing. If you were able to see my screen, the program that we flashed literally doesn't have any content. It's just like when you open Arduino IDE and you have a blank program, that's what's on the board right now. So now we're going to switch it to Tim's program, and we should observe a difference. Although we might need to slightly switch the frequency span that we're looking at in order to actually see it.
There's a thing.
Yeah. Pretty neat.
Yeah, so we see it, exactly. Yay. So here's a side channel. We can actually just visually identify whether the Arduino is doing nothing or whether it's doing whatever the specific program does. So it's pretty cool. Like,
So
we're not connected to the Arduino in any way itself. It's just all through the near field probe. This is radiation that's being created from the microcontroller.
I wanted to add, this is like the proof of concept, but for the like full paper that they submitted, they used like a TV antenna, one you would use to, so that's where you get the better distance. And then they can basically send packets by having like a little preamble that identifies the packet, like versus just normal stuff. And then there's like a specific like sync thing, and then you can read like a certain distance apart and get the data that way.
This is like for wireless communication.
Kind of, yeah. You can use
Via
it to like
side
send packets.
Oh, okay. Very fun. All right, cool demo.
Yeah, so that's it. Credit to Justin, Tim, and Professor Sahabach for this one.
Can you use this to bypass like air gaps devices? Is that possible?
I think that's basically the idea. Yeah, like you don't have to be physically connected. Observe through the electromagnetic side channels.
I think they're able to do it like through a wall too. Like a wall 6 feet, or I think 2 meters. So a wall 2 meters and then 2 meters on the other side of the wall. You can kind of.
Yeah, you just need the right antenna.
Read some EM.
So,
Oh yeah, you can kind of see the frequency, like the ramping of the frequency on the spectrogram. It's like very slightly ramping, but it's kind of there.
Are you able to switch that to the time domain? I wonder if you could. It's like a
well,
consistent.
No, you can't.
No, this is the spectrum analyzer, so no time.
Yeah, we don't have a real time one, unfortunately.
Makes sense.
Alright,
Yeah,
well,
one
I guess with that.
costs like $9 trillion. Wait, actually, we have the SDR. Could have used that.
Yeah, I think in some of the